Another day, another story. Quantum computing is a type of computing that uses quantum mechanical phenomena, such as superposition and entanglement, to perform operations on data. Quantum computers use quantum bits, or qubits, instead of classical bits to represent and manipulate data, which allows them to perform certain types of computations much faster than classical computers. These quantum algorithms are generally exponentially faster than their classical counterparts, allowing quantum computers to solve certain problems that classical computers cannot solve in a reasonable amount of time. There are several different types of quantum computing architectures, each with their own strengths and weaknesses. Some of the most common types include gate-based quantum computing. This type of quantum computer uses a series of quantum gates to manipulate qubits and perform operations on them. The most well-known example of this architecture is the IBM Q series of quantum computers. Topological quantum computing. This type of quantum computer uses anyons, which are quasi-particles that exist in two-dimensional systems, to perform operations on qubits. Adiabatic quantum computing. This type of quantum computer uses a process called adiabatic evolution to perform operations on qubits. Quantum annealing. This type of quantum computer uses a process called quantum annealing to find the global minimum of a function. D-Wave Systems is the most well-known company that produces this type of computer. All these architectures are still in the research stage and being developed. Some architectures are more suited for some specific use cases than others. Quantum computers work by using the principles of quantum mechanics, such as superposition and entanglement, to represent and manipulate data. The basic building block of a quantum computer is the qubit, which is the quantum equivalent of a classical bit. In classical computing, a bit can have one of two values, 0 or 1, and represents a single piece of information. In contrast, a qubit can exist in a state of superposition, meaning it can exist in a combination of the 0 and 1 states simultaneously. This allows a qubit to represent multiple pieces of information at once. The other key principle in quantum computing is entanglement, which refers to the phenomenon where two or more qubits can become correlated in such a way that the state of one qubit depends on the state of the others, even if they are separated by large distances. Quantum gates are used to manipulate the state of qubits and perform operations on them. These gates are similar to the logic gates used in classical computing, but they operate on qubits instead of bits. Examples of quantum gates include the Pauli gates, X, Y, and Z, the Atomar gate, and the Knot gate. Quantum algorithms are a set of instructions that are used to perform specific tasks on a quantum computer. These algorithms make use of the properties of qubits and quantum gates to solve problems that classical computers cannot solve efficiently. Some examples of quantum algorithms include Shor's algorithm for factoring large integers, Grover's algorithm for unstructured search, and the quantum Fourier transform for period finding. Despite the potential of quantum computing, it is still a very new and active field of research, and there are still many challenges to be overcome before practical quantum computers can be built. Some of the major challenges include developing stable qubits, developing quantum error correction, and developing quantum algorithms that can be run on practical quantum computers. Thanks for watching.